Good morning, everyone, and welcome to session 501, What's New with Core Audio. I am the first MC on the mic today. My name is Tori, and we have been very busy. We have a lot of interesting things to share with you today. We're going to start off by talking about some enhancements that we've made to Core MIDI and how that affects you and your apps. Then we'll move on to inter-app audio views, and then we will have a large section on the new, improved, and enhanced AV Foundation audio, and that will include a talk about the Audio Unit Manager, AV Audio Session, some utility classes, and that last bullet point there, AV Audio Engine, is such a large topic that it gets a session all to itself directly following this one in the same room, starting at 10:15 a.m. So, without further ado, let's talk about what's new with Core MIDI. If you have a studio, a music studio that you use to make music, it may look something like this. So maybe there's a Mac in the center of it, or an iOS device that are also very capable to be the center of your studio. And connected to it may be several USB MIDI devices, controllers, breakout boxes that are connected via 5-pin DIN to legacy equipment, musical instruments. And then also you may have a network session going. Well, beginning in iOS 8 and in macOS 10 Yosemite, your studio can start to look like this. So imagine after making a very quick Bluetooth connection, sitting down on a couch on the other side of the room of your studio and controlling all of your music. That's what you'll be able to do with MIDI over Bluetooth. So starting in iOS 8 and in macOS 10 Yosemite, you'll be able to send and receive MIDI data over Bluetooth low-energy connections on any device or Mac that has native Bluetooth low-energy support. The connections you establish are secure, meaning that pairing is enforced. No one can connect to your devices without your explicit consent. And after the connection is established, it just appears as an ordinary MIDI device that any application that knows how to communicate with the MIDI device can talk to. So to talk a little bit more about how this connection works over Bluetooth, I want to talk about the two key roles involved in a Bluetooth connection. There's the central and the peripheral. You already have some familiarity with this, maybe not with these names. You can view your central as like your iPhone and your peripheral as like your Bluetooth earpiece. The peripheral's job is to become discoverable and say, hey, I can do something, you can connect to me. So for Bluetooth MIDI, the peripheral side will advertise the MIDI capabilities. It'll say, hey, I can do MIDI, you can connect to me now. And then that side waits. The central can scan for a device that says they can do MIDI and then establish a connection. After that Bluetooth connection has been established, MIDI data can be shuttled bidirectionally between both of these. Now, in order to have a Bluetooth connection, you have to have one central, you have to have one peripheral, and we allow Macs and iOS devices to play either role. So you can connect Mac to Mac, iOS to iOS, Mac to iOS, and vice versa. So what does this mean for you and your application? If you are writing a Mac OS 10 application, the good news is you are already ready. Ready. This is the MIDI Studio panel from Audio MIDI Setup, which I'm sure you're all familiar with. If you look there, you'll see a new icon, the Bluetooth configuration icon. If you double-click that icon, you're going to get a new window. And this window will allow you to play either the central or the peripheral role. If you look at kind of the top third of the window, you'll see where there's a button that says Advertise. And click Advertise to become discoverable as Fresh Air. That's a name that you can modify. Fresh Air is the name of my MacBook Air because it's fresh. Then, the bottom two-thirds of it is the central view. If someone is advertising, hey, I can do MIDI, it will show up in the bottom. You click Connect to establish the connection. The pairing will happen, and then a new MIDI device will appear in the setup that any application that uses MIDI devices can see and communicate with. Now, on iOS, there is no audio MIDI setup. So how do you manage your Bluetooth MIDI connections? You'll be using new Core Audio Kit view controllers. There are two new Core Audio Kit view controllers that you can add to your application. One of them that allows you to play the role of the central, which means you scan and connect, and another that allows you to play the role of peripheral, which means you advertise and wait. If you establish a connection between two devices over Bluetooth MIDI, and they're not communicating for a while and they're unused by the application, after several minutes, we will terminate the Bluetooth connection to save power. So what does all of this look like in practice? I'm going to show you a short UI demo of how users would use this in their studios. Okay, I've got my demo machine ready here, and what I'm going to do is I'm going to launch Audio MIDI Setup. This is the audio window. We'll close this, and we will go to the MIDI window. Now, if you'll notice here in the MIDI window, there's this new Bluetooth configuration panel. So if I double-click this, then I will see that there are currently no advertising Bluetooth MIDI devices. I want my Mac to play the role as central, so I'm going to wait for someone to become available to connect to. And I'm going to use my iPad for that. So here's my iPad. And this is a little test application that we wrote to implement the Core Audio Kit view controllers that I talked about earlier. I'm going to go to Advertisement Setup, and this will give me the peripheral view. If you look here at the top, you see the name of this iPad Air is iPad Air MIDI. If I want to change this name, I could tap the I, but I'm okay with that name. And then I will say Advertise the MIDI service. Now, after I'm advertising the MIDI service, back on the Mac OS X machine, you'll see iPad Air MIDI has showed up here. If I click Connect, after a few moments, you'll see a new device appear in the MIDI setup. I'm going to launch MainStage because MainStage can receive MIDI notes and play back audio. Go into performance mode. Okay, so big confession here, I don't play keys. But I do have an application that plays keys really well called Arpeggio Gnome Pro. So I'm going to launch that, and I'm going to use it to send MIDI data over to the MainStage 3. Okay, now one thing I want to do really quickly here is check my connection status because I've left it inactive for quite a while here. So I'm going to go back and make myself advertise one more time. So now, this is live MIDI data being sent over Bluetooth. If I could get that volume a little louder, please. Thank you. So if I wanted to do this, preset is called Epic Fall, and it is epic. So that's Bluetooth being sent over MIDI, and also this sends not only the controller data, but it also sends the SysX data that you may have or any other type of MIDI. A few final words before I turn the mic over. This Bluetooth, being able to connect Bluetooth MIDI connections will work on both OS X Yosemite and iOS 8 using those view controllers that I told you about, and it will work on any Mac, iPhone, or iPad that has native Bluetooth low energy support. So now I'm going to tell you which ones those are. For Macs, any Mac that was manufactured in 2012 or later, and a mixed bag of Macs that were released in 2011 also have native Bluetooth low energy support. For the iPhone 4S and greater have Bluetooth LE. For the iPad, the first iPad with a Retina display has LE and the ones from that point, and all iPad minis have native Bluetooth low energy support. So this will work on all of those systems. Also, the connection is really low latency, it's very sensitive, and the Bluetooth LE bandwidth greatly exceeds the minimum MIDI bandwidth requirement for MIDI of 3,125 bytes per second. Standardization is in the works. We're working with standards bodies to standardize this so more people can get in on it. And the key takeaway for you is if you're making your iOS applications, please start adding these Bluetooth UI view controllers immediately to your applications so that users can manage Bluetooth MIDI connections using your app. And the person who's going to show you how to do that is my colleague and homeboy, Michael Hopkins. And I'll turn the mic over to him.
Thank you very much, Tori. I'd like to talk to you this morning about a new framework for iOS called Core Audio Kit. This framework provides standardized user interface elements for you to add to your application to do things like show the MIDI over Bluetooth LE UI that Tori just demonstrated, as well as some new views for those of you that are doing inter-app audio. We've designed these so that we do all the heavy lifting, so that you don't have to worry about rolling your own UI, and you can just concentrate on what makes your app unique. Therefore, they're very easy to adopt with a minimal amount of source code, and they work on both iPhone and iPad. Looking specifically about these interface elements for MIDI over Bluetooth LE, as Tori showed you, we have separated these into two different view controllers so that you can choose which one is appropriate for your own application, or you can use both. For example, if you use a UI split view controller, you can have those both visible at the same time. The first one is the CABT MIDI Local Peripheral View Controller. That's quite a mouthful this early in the morning. If you want to advertise your iOS device as a peripheral, you use this class. The source code for adopting this is very straightforward. You create a new instance of that view controller. Get the navigation controller object for your app and push that view controller onto the stack. The CABT MIDI Central View Controller is required if you want to discover and connect to Bluetooth peripherals. And you use that in the same way. You create the view controller and push it onto your view controller stack. Now I'd like to switch over and talk about inter-app audio. For those of you that weren't present last year at WWDC, we had a session talking about this new technology that we released with iOS 7. In review, inter-app audio allows you to stream audio between one or more apps in real time. A host application can discover available Node apps even if they're not running. And please refer to last year's session, What's New in Core Audio, session 206, for further details. But looking at how this works with the host app and a connected Node app, the Node app can be an instrument, an effect, or a generator, and the host app and Node app can send audio back and forth. In the case of an instrument, the host app can also send a MIDI to that instrument app and receive audio back. The two user interface elements that we provide in iOS 8 are firstly the inter-app audio switcher view, which provides an easy way to see all the inter-app audio apps that are connected together and switch between them using a simple tap gesture. We also provide an inter-app audio host transport view. This displays the transport of the host you're connected to in your Node app and allows you to control the transport, playback, rewind, and record, in addition to displaying where in the host transport you are via that numeric timecode. Now I'd like to show a demo of this in action. I have three different applications here that we'll be using together in our inter-app audio scenario. The first of which is GarageBand, which is the current version of that application that I've downloaded from the iTunes Store. I also have a delay application and a sampler. Let's take a look at the sampler first. This allows me to trigger sample playback via the keyboard. So now let's go ahead and connect this to GarageBand. I'm going to launch GarageBand. Going to connect to that sampler app. And now this is connected to GarageBand. So the first thing I'd like to demonstrate is that inter-app audio switcher view in action, which this application is implemented as visible via a button. I press that, and you can see now that we have two nodes shown, the host as well as our current application, and I can switch over to GarageBand simply by tapping. I'm going to add in an additional inter-app audio app, the delay effect. And now if I was to switch over to this application without using the switcher view, I could double tap on my home key, look and try to find that application. Where is it? It's difficult to find. And that's why we've provided the inter-app switcher view In this application, the delay, you can see that in the lower right-hand corner. And now that is showing our host, the sampler, as well as our current effect. So it's very easy to switch back and forth, and you can see that it just showed up there. So that's the first view I'd like to demonstrate. And if I play back on my keyboard, we can hear that we're now getting that delay. And this is interesting because we have, we're sending audio from the host to our sampler and then through an effect applying that delay and then back. Now the second view, the transport view, you'll see just above that view. Let me hide that for you. And that allows me to control the transport of the host. I can do recording. Sorry, I'm no Dr. Dre. It's too early in the morning for that. But you get the idea. And these are the views that we're providing for your benefit. So please adopt those to add this functionality to your application. Okay, so the goal between these user interface elements are to provide a consistent experience for your customers. You do have some flexibility in controlling some of the visual appearances of those controls. They support a number of different sizes, so if you want a ginormous UI, you can have that, or if you want them very small, you can do that. The source code, as I'm going to show you, is very easy to add to your application. And because these are subclasses of UI view, you can choose to create a view controller if you want to add them to a UI popover view on your iPad, or if the example demonstrated, if you want to embed that directly in the content of your app, you can do that as well. Let's take a look at the code. We import the umbrella header. In this case, I'm demonstrating how to add the switcher view from a nib file. So you go into IV, drag out your UI view, assign that to be the class of the C8 Interapp Audio switcher view, create an outlet for that view, and then in the viewDidLoad method, we specify the visual appearance of that view, and then we need to associate an audio unit with that view so that it can automatically find the other apps that are connected. And that's all there is to it. And creating the transport view programmatically, as this example shows, we create the view, specify initial size and location of that view, configure its visual appearances, associate an output audio unit with the view, and then finally we add that transport view as a subview of our main content. Okay, now I'd like to switch gears a little bit now back to AV Foundation. The rest of my presenters, including myself, will be focusing on this framework and some of the new enhancements and abilities that we've added for you to add to your application. The first new feature is for audio unit management, and that's the AV Audio Component Manager. This is a macOS 10 Yosemite API, Objective-C based, and it's primarily designed for audio unit host applications. However, as you'll see, we do have some end-user features as well. We provide a number of different querying methods which enable your host to find the audio units on the system given some criteria, for example, number of supported channels. We have a simple API for getting information about each individual audio unit. We have some new tagging facilities that I'll demonstrate in a moment. And finally, we have a centralized audio unit cache, so that if you have multiple host applications on your system, once one host has scanned audio units, and for a lot of people they have a large number of them, so this can take quite some time, all the other hosts on the system share that information so they don't have to perform that exhaustive scan again. Let's take a look at the API in more detail. As I said, these are an AV Foundation and they're new. The first class is the AV Audio Unit Component Manager, and this provides 3 different search mechanisms for finding audio units, the first of which is based on the NS predicate. We can use a SQL-based language to provide strings, which I'll show you in a source code example later, for finding audio units matching a given criteria. We also have a block-based mechanism for finer programmatic control. And for those of you using older host apps, with our current audio component API, we have a backwards compatibility mode as well. Each of these search methodologies return an NS array of AV audio unit components, and that class can be used to get information about the audio unit. Now, using our prior API, if I wanted to do something like find all stereo effects that support 2-channel input and 2-channel output, I'd have to write a great deal of code. That's okay, but now with this new API, we can reduce all that to this simple, elegant 4 lines of code. The first of which is retrieving an instance of the shared audio unit manager. And here I'm using the block-based search mechanism to find all components that pass a specific test. And in this block, I'm checking to see if the type name of that audio unit is equal to the preset string AV audio unit type effect. And then furthermore, we're checking to see if that audio unit supports stereo input and output. You'll notice there is a stop parameter, so if you wanted to return only the first instance of the audio component matching this criteria, you could return yes, and the stop would stop immediately. Okay, now I'd like to move on to talk about tagging. A lot of people, especially Dr. Dre in his studio, has a large number of audio units. So finding the right one can be a bit challenging because they're sorted alphabetically or by manufacturer. And there's a lot easier way for users to find these audio units now with tagging. It's very similar to what we've done with a Finder, the previous macOS 10 release. Users can now specify their own tags with an audio unit in order to create broad categories or even specific categories of how they want to organize their audio units. They can apply one or more tags in 2 different categories, the first of which is a system tag. This is defined by the creator of the audio unit. And for example, in Yosemite, I have to get that name in my head. I personally liked weed, but I didn't get to vote. The system tags are defined by the creator, and we as Apple have added standard tags to all the audio units that we feel would be useful to most of our users. You can also have user tags. These are specified by each individual user on the system. So if you have 3 users, they can each have their own set of tags. A tag is a localized string in the user's own language. Swedish, Swahili, doesn't matter. They can be arbitrary, or they can be a predefined type, and these are all in audiocomponent.h. They can be either based on the type of audio unit, for example, a filter or a distortion effect, or they can be based on the intended usage, for example, an audio unit useful in a guitar or vocal track. Now I'd like to show a demo of tagging in action using a modified version of AU Lab. So in AU Lab, we can look at all the tags associated with all the built-in audio units. And here you see that, for example, the AU time pitch has 2 standard tags that are associated with it, time effect and pitch, and those are defined by us. In addition, you can see that this distortion effect has 2 user tags, one specifying that it's useful for a drum track and another one for a guitar track. The API also provides developers the ability to get a list of all the system-defined tags localized in the language of the running host, as you can see here. And I can also see all of the user tags that the users assign to all the audio units on the system. Adding tags are as simple as typing a new one. Now that's been added to that audio unit. And I can do a search using those predicate-based and other search mechanisms, and it will search all the audio units looking for that particular tag. So this is something that's really exciting, and we hope that you'll use this API to add tagging functionality to your own host application. Let's take a look now at the API. To find an audio unit with a specific tag, in this example, I'm going to use the NS predicate filtering mechanism. Here I'm defining a predicate. It says that the component has to have the all tag names property containing a particular string, in this case, my favorite tag. And this is the identical search string that you just saw in my demo. Once you've defined the predicate, you get an instance of the shared AU manager, and then call components matching predicate, which returns an array. To get a list of the tags associated with this particular AV audio component, you use the user tag names property. You can assign to that as well. And in this example, I'm adding 2 tags to the audio unit. We can get all tags for a specific component, and these will include the user tags as well as the system tags, all tag names property. We can get a localized list of all the standard system tags by getting the component manager and then calling the standard localized tag names property. This is what I was displaying in the pop-up in my demo. And finally, I can get a list of all the localized tags that the user has assigned across all the audio units on the system. And that, again, you saw in my demo. For those of you that ship audio units and you want to add your own built-in tags to those audio units, you need to go into your audio component bundle and in your info.plist, look at your audio component dictionary and add a tags section. These first 2 items are examples of using standard tags. And the third item is a custom tag. So you can have that be something meaningful to your own company. For example, if you have a suite like the Silver effect package, you could add that tag. If you do so, you can also localize that tag by adding an audio units tag.string file into your bundle, and then adding localizations for each language that you wish to support. And please do not localize any of our stand-in system tags. We've already done so for you. So in summary, if you're a host developer, please adopt the AV Audio Component Manager API so your users can tag all their audio units. And if you're an audio unit developer, please add system tags to your audio units. So without further ado, I'd like to turn over this session to Eric Johnson, who will be discussing tips and tricks and new functionality in AV audio session. Eric?
Michael? Good morning. So I'll be continuing on with the AV Foundation framework. This time we're on iOS only with AV audio session. So today we're just going to spend a few minutes talking about some best practices, focusing on managing your session's activation state, and then also talking about just a little bit of new things in iOS 8. Before we dive in, I wanted to call your attention to an updated audio session programming guide that's available on developer.apple.com. Since we saw you all last year at this time, this guide has been updated so that it's been rewritten in terms of AV audio session, so it's no longer referring to the deprecated C API. That's a really great update. And for those of you who are maybe not that familiar with audio session, there was a talk from 2 years ago where Tori talked about audio session and also multi-route audio in iOS. All right, so let's dive into talking about managing your session's activation state. So there's your application state, and then there's your audio session state, and they're separate things. They're managed independently of each other. So if you've been doing development for iOS, you're probably familiar with app states. So this is whether your app is running or not, whether it's in the foreground or the background, if it's been suspended. Your audio session activation state is binary. It's either inactive or active. Once you've made your session active, you do need to be prepared to handle interruptions, and we'll talk about what that means. So let's look at an example of how an audio session state changes over time. So here, we're on an iPhone. We have our application on top, our audio session. Let's say that we're developing a game app. And then on the bottom, we have the phone's audio session. And right now, the user's not in a phone call. and they haven't launched our app yet. So both sessions are idle, inactive. So now the user launches our app. When we first come into the foreground, our audio session is still inactive. And because we're a game app, we want to make our session active when we're in the foreground so that we can be ready to play audio. So we'll do that. And we're going to just play some music. So we're now happily playing music in the foreground with an active audio session. So then the phone starts ringing. We get interrupted by the system sends us an interruption event. The phone's audio session becomes active and plays the ringtone. And the user decides to accept the call. So the phone's audio session stays active, and our audio session has been interrupted, so we're inactive. And then the user ends the call, hangs up, says goodbye. And now the system is going to deliver an end interruption event to our audio session. And we're going to use that as a signal to make our session active again and resume playback. And we continue in this state. So this is a typical example of how something like a game application interacts with the phone app's audio session on an iPhone. So the way that you need to manage your application's audio session state is actually going to depend on how you use audio. We've identified a number of different types of applications that commonly use audio on iOS. And we don't have time to talk about all these this morning, and you'd probably be bored to death if we did. So we're just going to talk about a few of these. So let's continue on with the idea that we're developing a game app. So for game apps, usually what we recommend is that when you're in the foreground, you'll want to have your audio session active. So a good place to make your audio session active is in the app delegate's application to become active method. So that will cover the case when you're being launched, if you're coming from the background into the foreground, or if you were already in the foreground and the user had swiped up the control panel and then dismissed it. You'll be covered in each of those cases. So once you've made your session active, you can leave it active, but you do need to be prepared to deal with interruptions. So if you get a begin interruption event, you should update your internal state so that you know that you're paused. And then if you get an end interruption event, that's your opportunity to make your session active and to resume audio playback. And this is just like the example that we looked at just a few minutes ago. Media playback apps need to manage their audio session state a little bit differently. So I'm talking about applications like the built-in music app or podcasts or streaming radio. And these are the types of applications that will usually have a play-pause button, and they're what we refer to as non-mixable, meaning that they'll interrupt the audio of other non-mixable audio sessions. So for these types of applications, we recommend that instead of making your session active immediately when you enter the foreground, that you wait until the user presses the play button. And the reason that we give you that advice is sometimes the user brings your app into the foreground just to see if they have a particular podcast episode downloaded or to see if they have a song in their library, and they don't necessarily want to interrupt other audio that was playing. So it's good to wait until they press play. So like in the case of a game app, once you've made your session active, you can leave it active. But again, you need to be prepared to handle interruptions. So if you get a begin interruption event, you should update your UI. So if you have a play-pause button, it's a good time to change that state. And also keep track of your internal state so that you know that you're paused. One thing you do not need to do is you do not need to make your session inactive because the system has already done that for you. That's what the interruption is. So then, if you get an end interruption event, we ask that you honor the should resume option. So if this option is part of the info dictionary that's part of that notification, that's the system giving you a hint that it's okay to make your session active and to immediately resume playback. If you don't see that option as part of the notification, then you should wait for the user to press play again. Okay, so we've talked about for game apps and media playback apps when you would make your session active. What about making your session inactive? So if you're something like a navigation or a fitness app, you're typically going to be playing short prompts of audio. And you're going to be using the Duck Others category option, which will lower the volume of other audio applications on the system. So it's important that when you're done playing your short prompts that you make your session inactive so that the other audio is able to resume at full volume. If you're a voice over IP app or a chat app, or maybe one of these apps that has like kind of a browser view where you're playing short videos, then you're usually going to be what we refer to as non-mixable, meaning that you're going to interrupt other audio. And so it's important that when you're done playing audio that you make your session inactive so that other sessions are able to resume. And it's a good idea to use the Notify Others on Deactivation option when you make your session inactive. And that way the system is able to tell an interrupted audio session that it's okay for them to resume. All right, so now let's shift gears a little bit and talk about managing your secondary audio in response to other audio on the system playing. So first, let me explain what I mean by secondary audio and primary audio. So let's say we're developing a game application. Our primary audio is going to be our sound effects, our explosions, beeps and bloops, short bits of dialogue. And it's the kind of audio that really enhances the gameplay. And it's also the kind of audio that if the user was listening to music when they launched your app, you still want it to play, and it's okay that it mixes in with the other music. By secondary audio, I'm really talking about your soundtrack. This is the audio where it also enhances the gameplay, but if the user was previously listening to their music or their podcasts, you'd just as soon have your soundtrack be muted. And then if the user stops their music playback or their podcast, then you'd like to have your soundtrack resume. So in iOS 8, we've added a bit of new API to help you do this. We've added a new property and a new notification. The property is called Secondary Audio Should Be Silenced Hint. As the name implies, it's a hint that the system is giving you that it's a good time to mute your secondary audio. So this is meant to be used by apps that are in the foreground. And we recommend that you would check this property in application did become active. Going along with the new property is our new notification. This is the AV audio session silence secondary audio hint notification. Another mouthful for this early in the morning. So this notification will be delivered to apps that are in the foreground with active audio sessions. And it's kind of similar to our interruption notification in that it's two-sided. There's a begin event and there's an end event, all wrapped up in the same notification. So when you get a begin silence secondary audio hint notification, that means it's a good time to mute your secondary audio. And if you get the end event, it's a good time to resume your soundtrack. So let's look at what this looks like in action. So on the far right, we have the built-in music app, and it's currently in the background. It's not playing audio. On the far left, we have our game app that we're developing. So we're playing our primary audio, the sound effects, and we're also playing our soundtrack because there was no other music playing. And in the middle, we have iOS helping to negotiate things. So the user has his headphones plugged in, and he presses that middle button, and the music app responds to remote control events, so it uses that as a signal to begin playback. The music app also informs iOS that it's using its audio output, and so then the system is able to send a begin notification to our app that's in the foreground. And in response to that, we can mute our soundtrack. So our app is still in the foreground. The only thing that's really changed is that the user used their middle button to play their music, and we've responded to the notification that we got from the system. So now some time passes. We're in this state for a while, and the user presses the middle button again. So the music app responds by pausing its playback and telling the system that it's pausing its audio output. And then the system is able to send the end notification to our app that's still in the foreground. And in response to that, we resume our soundtrack. So hopefully this will be pretty easy to use. There's one new property and then the two-sided notification that you can use to manage your soundtrack. So kind of on a similar thread, in the past we've given advice about how you could manage your secondary audio based on the is other audio playing property. And we had given advice about choosing between the ambient category or solo ambient based on the state of this property. What we're recommending now is that if you're this type of application, that you just use the ambient category and then use the new property and the new notification to manage your soundtrack. All right, I'm going to hand things over to Doug Wyatt, who's going to tell us about some new utility classes in AV Foundation.
Thank you. Good morning. I'm Doug Wyatt. I'm an engineer in the Core Audio group, and I'd like to talk to you about some new audio classes in the AV Foundation framework. We'll start out with some background and tell you what we're up to and why. Then we'll start looking through these classes one by one, and I'll tie things up at the end with an example. So in the past, our Core Audio and Audio Toolbox APIs, they're very powerful, but they're not always easy for developers to get their hands around at the beginning. We've tried to work around this by providing some C++ utility classes in our SDK, and that's helped to some extent. But example code gets copied around, it evolves over time. And we think it's best in the long run if we sort of solidify these things in the form of API, and that's what we're providing now with these classes in the AV Foundation framework, starting with macOS 10, 10, 10, 10, 10, and iOS 8. So our goals here, we don't want to make a complete break with the past. We want to build on what we've already got. We're going to, in many cases, wrap our existing low-level C structures inside Objective-C objects. And in doing so, these lower-level C structures become easier to build, but we can also extract them from our Objective-C objects and pass them to the low-level APIs we might already be using. And this is a philosophy we use also with the AV Audio engine, which we'll be examining in more detail in the next session here. And I should also mention an overriding goal here is for us to stay real-time safe, which isn't always easy with Objective-C. We can't access methods or properties on the audio rendering thread. So we've taken some great care to do that in our implementations. And as we go, I'll give you a couple of examples of places where you need to do this to be aware of real-time issues when you're using these classes. Okay, so here are the classes we'll be looking at today in this session. At the bottom there, in green, we've got AV Audio Format, which has an AV Audio channel layout. In blue, we have AV Audio PCM Buffer, which has an audio format. Every buffer has a format describing it. And finally, we'll be talking about AV Audio File, which uses AV Audio PCM Buffer for I/O. And as you would expect, a file also has format objects describing the file's data format. So first, let's look at AV Audio Format. This class describes the actual format of data you might find in an audio file or stream, and also the format of the audio you might be passing to and from APIs. So our low-level structure here for describing an audio format is an audio stream basic description, which in retrospect might have been called audio stream not so basic or audio stream complete description, because there are a lot of fields there, and it can be a little challenging to get them all set up consistently, especially for PCM formats. But the beauty of this structure is that it describes just about everything we would want to use to describe an audio format. But again, it's a little challenging. But in any case, you can always create an AV Audio format from an audio stream basic description, which you might have obtained from a low-level API. And you can always access a stream description from an AV Audio format. But now we can move on to other ways to interact with AV Audio format. So in the past, we've had this concept of canonical formats. And this concept goes back to about 2002 in macOS 10.0 or 10.1 or so. So this format was floating point, 32-bit, de-interleaved. But then we got along to iOS, and we couldn't really recommend using float everywhere because we didn't have the greatest floating point performance initially. So for a while, canonical was 8.24 fixed point. But because of that schism, we want to reunite under something new now. We've deprecated the concept of canonical formats. And now we have what we call a standard format. We're back to non-interleaved 32-bit floats on both platforms. So this is the simplest way to construct an AV audio format now, is with, you can create a standard format by specifying just a sample rate and channel count. You can also query any AV audio format you might come across and find out if it is a standard format using the standard property. We've also provided for using common formats with AV audio format. And we define common formats as formats you would often use in signal processing, such as 16-bit integers, if you've been using that on iOS or other platforms. We also provide for 64-bit floats. It's very easy to create an AV audio format in one of these formats by specifying which one you want, the sample rate, channel count, whether it's interleaved. You can query any format to see if it is some common format or something else using the common format property. Okay, so that's AV audio format. Let's look at AV audio channel layout. Briefly here, this describes the ordering or the roles of multiple channels, which is especially important, for example, in surround sound. You might have left, right, center, or you might have left, center, right, and so on. It's important to know the actual order of the channels. So every AV audio format may have an AV audio channel layout. And in fact, when constructing an AV audio format, if you're describing 3 or more channels, you have to tell us what the layout is. So it becomes unambiguous to any place else in the system that sees that AV audio format what the order of the channels are. So the underlying audio channel layout object is pretty much exposed the way it is here. You can go look at that in coreaudiotypes.h, but we have wrapped that up in AV audio channel layout for you. Okay, moving on. Let's look at AV audio PCM buffer. So buffer can be a sort of funny term when we're dealing with deinterleaved audio because of the audio buffer list structure. But that aside, you can think of it simply as memory for storing your audio data in any format, including non-interleaved formats. And here are the low-level structures, which these ones in particular can also be a bit of a bother to deal with because audio buffer list is variable length. So you can simply create an AV audio PCM buffer. It'll create an audio buffer list for you of the right size. And you can always fetch it back out of the AV audio PCM buffer. Here's the initializer. So to create a buffer, you specify the format and a capacity in audio sample frames. You can always fetch back the buffer's format and the capacity with which it was constructed. And unlike audio buffer list, which has a simple byte size for every buffer, here we've separated the concepts of capacity and length. So there's the fixed capacity it was created with, and the frame length, which expresses the number of currently valid frames in the buffer. Some more methods here. To get to the underlying samples, we provide these simple type-safe accessors. And this is a good time now to say a word about real-time safety, because these are properties, and as useful as they may be for actually getting to the data, since they're properties, they may involve a method lookup, which can, in principle, take a miss on the lookup and cause you to block. So if you're going to be using AV audio PCM buffers on audio real-time threads, it's best to cache these members in some safe context when you're first looking at the buffer, and use those cached members on the real-time thread. Okay, that's PCM buffer. Now we can look at audio file, which wraps all these other classes together. So here we let you read and write files of any core audio supported format. This ranges from M4A, MP4, WAV, CAF, AIFF, and more I can't think of right now. So in accessing the file here, we give you a single way to read and write the file completely independent of the file's actual data format. So if it's an encoded format like AAC or Apple Lossless or MP3, if there's a codec on the system, and in most cases there is, we will transparently to you decode from that format as you read the file. Similarly, when you're writing an audio file, we will encode from PCM into that encoded format if we have an encoder. So to do this, the file has this concept of the processing format. And the processing format is simply the PCM format with which you will interact with the file. So you specify the PCM format when you create the file, and it has to be either a standard or common format. The only limitation here is that we don't permit sample rate conversion as you read from or write to a file. Your processing format needs to be at the same sample rate as the file itself. Now, if you're familiar with the Audio Toolbox Extended Audio File API, this is functionally very similar. It's just a bit simpler to use. So looking now at the initializers and some accessors for AV audio file, here's the initializer for reading from a file. If you don't specify a processing format, you simply you get the default behavior, which is that your processing format will be a standard format. Very similarly, to create an AV audio file for writing, the only extra information you need to give us is a settings dictionary. This is the same settings dictionary passed to AV audio recorder. And in there are keys which specify the file format you want to use. And in the case of, for example, AAC, you can specify the bit rate and any other encoder settings. Those are in the settings dictionary. So once you've built a file, you can always access back the actual file format on disk. So that might be, for example, AAC, 44 kilohertz, 2 channels. But you can also query the processing format with which you created the file. And in the case of these two simplest initializers, those would be floating point 32-bit, same sample rate as the file, same channel count as the file. Okay, so to read and write from AV audio files, there's a simple method, read into buffer, and that will simply fill the AV audio PCM buffer to its capacity, assuming you don't hit the end of file. Write from buffer is a little different in that it looks at the buffer's frame length rather than the capacity, so it writes all of the valid frames from that buffer to the file. And you can do random access I/O when reading from audio files. So this is like the standard C libraries seek and tell functions, fseek and ftell. You can query the frame position to see where you are when reading an audio file. And you can also seek to a different position in the file by setting the frame position pointer before you read. And the next read will proceed sequentially from that point. Okay, I'd like to tie all these classes together now with a short example. In about 4 screens here, we'll see what it's like to open an audio file, extract some basic information from it, and read through every sample in the file. So here we have init for reading. We simply pass a URL. I'm using the variant here that's explicit, but I'm passing PCM float 32 anyways. I could have left those off and gotten a standard format. I'm going to fetch some basic information from the file and print it, including the files on disk format and the processing format. I can query the audio file's length in frames, sample frames, and I can convert that length in frames to a duration by dividing by the file's sample rate. Okay, next I'm going to create a PCM buffer to read from. Since the file might be large, I don't want to try to read it all into memory at once, so I'm going to loop through it 128K sample frames at a time. So I'm going to create a buffer with that capacity. And notice I'm just going to pass the audio file's processing format when allocating this buffer, and that ensures that the buffer is the same format that the file will be giving me. And here I'm ready to start reading through the file, and I'm going to read one buffer at a time until I get to the end. So I can query the current frame position and see if it's less than the length I discovered earlier. I can read into buffer, which will again fill the buffer to capacity. I can double check to see if I'm done by seeing if I got a zero length buffer. And this is a lot of code, but it boils down to 2 for loops. The outer one is walking through all of the channels in the buffer if it's a multi-channel file. And then the inner loop will look at every sample in that buffer. So given every sample, I can look at its absolute level and see if it's the loudest sample, or if it's louder than the loudest sample I've found so far, and if so, I can record that level and where I found it in the file. So there, in about 4 screens of code, I opened an audio file, I read through the whole thing one sample at a time. Okay, so moving on, I'd like to just sort of foreshadow the uses of these classes in the AV Audio Engine session, which will follow this one. So at the bottom we see AV Audio File and AV Audio PCM buffer, and those are both used by something called AV Audio Player Node, which will be your basic mechanism for scheduling audio to play back. AV Audio Player Node is a subclass of a more generic AV Audio Node class, which is some unit of audio processing. And we'll see how AV audio formats are used when describing how to connect AV audio nodes. So that brings us to the end of my section of this talk. We saw the AV audio format, channel layout, PCM buffer, and file classes. You can use these without AV Audio Engine using your existing code with the Core Audio, Audio Toolbox, and Audio Unit C APIs if you're careful to stay real-time safe, and you can use those accessor methods to extract the low-level C structures. And again, we'll be seeing how these are used in more detail in the next session on AV Audio Engine. And that's the end of our hour here. We've looked at MIDI over Bluetooth, the Interapp Audio UI views, lots of features of AV Foundation Audio, and we hope you'll stick around for the next session on AV Audio Engine. If you need more information, Philip is our evangelist, and there are the developer forums. Here's the next session I keep talking about.